Today we're going to be building a spreadsheet model for the Ethiopian wolf population. In particular, we're going to do a population viability analysis, or PVA for short. Jed mentioned that PVAs are used so that a biologist can make a statement such as the Ethiopian wolf has a 95% chance of surviving for the next 20 years. He also reviewed some very basic population parameters that are used in a PVA. And today we're going to build probably the simplest PVA that you can possibly build. They can get really complex, but we're going to stick with simplicity just to get the idea of what a PVA is and how it is used. Jed mentioned that there are two key parameters in modeling populations, the per capita birth rate and the per capita death rate. For the wolf population, let's assume that the per capita birth rate is 3 individuals, 3 pups per adult female or per female, and that the death rate is 2.7. R, capital letter R, is the geometric rate of increase, and that's just the difference between the birth rate and the death rate. So if the birth rate is greater than the death rate, R will be positive, greater than 0, and that means the population is growing. This actually gives the rate of increase, so this population would be growing at 30% per year. If R is 0, that means the birth rate and the death rate match each other and the population is stable. And if R is negative, then the population is declining. Lambda is the geometric growth rate plus 1, and Jed did the derivation for that as well. And this is what we'll be using when we model our PVA. When we do a PVA, we're going to start with a starting population, and we'll start with 84 individuals. And here we need to enter the average lambda and the standard deviation for lambda for this population. So in cell C7 we'll simply reference cell E4, and then we'll enter a standard deviation in cell D7. What this means is that the wolf population on average has a lambda value of 1.3. That's your average year. Not every year has that value. In some years lambda can be greater, in other years it can be less, but the overall average is 1.3. The standard deviation, as Jed mentioned, tells you how variable, how far away from this 1.3 are the numbers that we can draw. How variable is lambda from year to year? That's what that's really getting at. Now, to give you a sense for what this distribution looks like, we've set up a series of numbers here called x. This would be an example of lambda. And we're going to ask, what is the probability of drawing a negative 2.5 from a normal distribution whose mean is 1.3 and whose standard deviation is 0.4? In Excel, we're going to use the function called normDist, and you can find this by just searching for the function, and you'll find it right there, norm.dist. And what this function has is it has 4 arguments. The first one is x. We're going to let x be referenced in cell M4. So that's just saying, what is the probability of getting a negative 2.5, x is equal to 2.5, for a normal distribution that has a mean that's referenced in cell C7, and we'll anchor this reference, and the distribution has a standard deviation of D7. We want the exact probability, so we're going to enter the word false in for the last argument, and then we press OK. Now we can copy this through, and we're given a distribution of what a mean is. What does a normal distribution look like when the mean is 1.3 and the standard deviation is 0.4? and this is what it looks like. Later, we're going to ask that you change these values to get a good handle on what they really are meaning. But for now, let's just say that the mean is 2, and you'll see the graph shift over to the right, and we would expect that we should extend this series down so that we can see the whole distribution. So we'll go back to 1.3, but let's now change the standard deviation. If the standard deviation is small, say 0.1, our distribution will get tighter. So here it's ranging between 0.1 and 2, whereas our original value, it ranged between a little bit above 0 and 2.5. So the larger the standard deviation, the more spread out this curve becomes. Now, normal distributions have this bell-shaped curve. You're probably familiar with this distribution. The center of this curve is the mean. So the peak of this curve is centered directly on the mean value. And again, the standard deviation controls the spread of the data around that value. So these two inputs here are the parameters of the normal distribution. Now, to give you a little bit of sense of what this distribution feels like, we're going to let you enter a percentile in here, say 0.95, and we'll go back, and then we'll figure out what is the probability, what's lambda, associated with 95% of the curve. So if we look at all of these lambda values that are possible, and we want to know which lambda value has 95% of the values below it, we're going to be able to use another function that's associated with the normal distribution, and that's, let's just type in norm, and we'll get a list of all the distributions. This one is called norm inverse, norm.inv. Here we're going to say what is the 95, the probability is going to be 0.95, so that's what we're putting in right here, when the mean is 1.3 and the standard deviation is 0.4. So what this function is doing is it's saying, I want to know what the lambda value is when the probability is 0.95. And when we look at this curve, what that means is, let's zoom out to 1.96, which is right here, 1.96, and that means that 5% of the lambda values are greater than this number, 1.96, and all of the other values, 95% of the values, are less than 1.96. Hopefully that makes some sense. Let's try another one, 0.5. When the percentile is 0.5, we're asking what value of lambda falls so that 50% of the curve is above it and 50% of the curve is below it. And we're back with our mean value, 1.3. That's because we're centered directly over 1.3. I encourage you to pause your video and play around with these percentiles. You can enter any number between 0 and 1, and 0 and 1 exactly might give you an error, but anything in between there will give you a lambda value. And just remember what this is saying. It's giving you the lambda value on the horizontal axis, and it's telling you how much of the data is to the right and how much of the data is to the left of that value. Now this is handy for us to know because this gives us a sense that some values, if we pick them at random, which we'll do in just a minute, are much more likely to be drawn than others. So for this distribution, which would you say is more likely for us to draw? A 1 or a 2.5? Well, a 1 has a much higher probability of being drawn than a 2.5. And so when we draw from this distribution, we'll find that most of the numbers fit squarely within this big heavy area here, but occasionally we'll draw numbers out on these tails. And the way we're going to draw these numbers is with yet another function. In particular, another norm inverse function, but this time we're going to throw a little twist on it. So let's go back to our norm inverse function, and this time we're going to draw a random probability. And in Excel, we can designate a random number with RAND, open parentheses, close parentheses. Once again, our mean is going to be referenced in cell C7, and our standard deviation is going to be referenced in cell D7. You'll see that Excel returns the word volatile here, and that means that every time the spreadsheet is calculated, a new random number is drawn. Let's try it. Here's a lambda value that we drew. This is just a random deviate that's drawn from this distribution. And we happen to draw a 0.8 because of the random number that was associated with it. If we press F9, here's another random lambda. This one's 1.36, so someplace right around here. Here's 0.94, 0.62, 1.06, 1.79, 0.67, so we're really staying around this main region here. But you'll see if we keep doing this, we'll occasionally get these outer tails. Now, to make this even more clear, let me put a random number in this portion right here, so you can see what the random number is. And then instead of referencing the random number here, let's reference this random number so you can see exactly what it's referring to. So the random number of 0.41 corresponds to a lambda value of 1.22. Press F9. A random number of 0.09 corresponds to a lambda value of 0.76. Hopefully this is making some sense, and we're going to be using this norm inverse function along with a random number to simulate the wolf population through time, given that the mean is 1.3 and the standard deviation is 1.4.